The fourth principle, very much related to the third in our series of the guiding principles of scientific inquiry, the fourth principle is about the chain of reasoning and coherent and explicit chain of reasoning. And can be a very difficult one for new scientists and for graduate students who are just learning. So let's get into it. So the fourth principle and the third are really, really strongly related to each other because it's often the method used that also helps to provide or helps to guide the sort of thinking and reasoning about why you see the results that you do in the study or the analysis that you're working on, and what this says about the theory you're working with or what theories are related to it and all this kind of thing. So this is a really important, this might be a bit longer because there is a lot that goes into with the idea of coherent, explicit chain of reasoning that needs to be a part of scientific inquiry. You can't just make things up. You got to have reasons for things. You got to be able to follow back and forth and what have you, and not necessarily fully linearly necessarily, as some things don't necessarily have to be fully linear in their relationships to each other. So in that line of reasoning, but you do have to have a coherent line of reasoning that can get you from one end to the other and go back, actually. So let's get into it. The extent to which inferences that are made in the course of scientific work are warranted depends upon the rigorous reasoning that systematically and logically links the empirical observations with the underlying theory and the degree to which both theory and observations are linked to the question or problem that lies at the root of the investigation. There is no recipe for determining how these ingredients should be combined. Instead, what is required is the development of a logical chain of reasoning that moves from evidence to theory and back again. The chain of reasoning must be coherent, explicit, so that another researcher could replicate it, and persuasive to the skeptical readers, so that, for example, counter-hypotheses are addressed. So these three things are the basic kinds of things that we look for in the reasoning that goes into scientific inquiry. The reasoning of an argument that you might find in a peer-reviewed journal or in a report or any number of different things where you see a scientist speaking, they have to have reasoning that goes coherently back and forth from one thing to the other. Another way to look at this is that we try to avoid logically fallacious reasoning. For example, in critical race theory, for instance, it is often used as a logically fallacious argument that is often used that because disparity, therefore discrimination is the reason. That is a logical fallacy. It is an if-then logical fallacy. I covered this in the review of the Nature Communications article by Hendrada Ali, or led by Hendrada Ali, I should say. And that logical fallacy is there. I won't go into that more here. But that's the things you want to avoid. You want to avoid circular reasoning. Here, you want to avoid that kind of problem too. So logical fallacies are things we tried to avoid here. So you have a logical chain of reasoning that moves you from one thing to another, and back again. All rigorous research, quantitative and qualitative, embodies the same underlying logic of inference. This inferential reasoning is supported by clear statements about how research conclusions were reached, what assumptions were made, how was the evidence judged to be relevant, how were alternative explanations considered or discarded, how were the links between data and the conceptual or theoretical framework made. The nature of this chain of reasoning will depend on will vary depending upon the design of the study, which will in turn vary depending upon the question that is being investigated. Will the research develop, extend, modify, or test a hypothesis? Does it aim to determine what works? How does it work? Under what circumstances does it work? If the goal of the research is to test a hypothesis stated in the form of an if-then rule, successful inference may depend upon measuring the extent to which the rule predicts the results under a variety of conditions. If the goal is to produce a description of a complex system, such as a subcellular organelle or a hierarchical social organization, successful inference may rather depend on issues of fidelity and internal consistency of the observational techniques applied to diverse components and the credibility of the evidence gathered. The research design and inferential reasoning it enables must demonstrate a thorough understanding of the subtleties of the questions to be asked and the procedures used to answer them. So that's the thing. The inferential reasoning is where you really prove that you know what you're doing. In a lot of ways as a scientist, if you can go from point A to point B with your reasoning and make it very clear that this is why these things happen and this is why these other counter things don't work necessarily, then you can really make your case. And that is the biggest probably one of the most important things that gets really, really ignored a lot of times, and particularly nowadays with all the woke nonsense that's going on. The importance of having clear, coherent reasoning for every question, for for your method, and what have you, for your analysis and inquiry is incredibly important to actually make your case, and make it so that somebody else can understand it and be disproven by it. In a lot of the cases with the woke nonsense, it's unfortunately involves psychological and emotional manipulation is where they go. That's not good science and good scientific inquiry. That has no place in such inquiry here. So again, that's another reason why critical race theory and critical theory is anti-science, but that's a whole other video that I already did. All rigorous research. Okay. So yeah, you have to make this chain all the way through from beginning to end. This is what we observed. You know, why does it prove or disprove your theory, and how did you get into other things? Often, this is very connected with the method that's used in the analysis. You will use a method that tests something specifically, but you may also use a method as part of the study, or an additional method to your own original method that shows why something else isn't the reason why. And often the single method that you use, if you're constructing method carefully and considering that, you can get at the things like, well, this method shows that this thing works, but it also shows that this thing couldn't possibly work because, say, if you did, for example, a regression between multiple different variables and what have you, and you included something that could have been a counter to it, where somebody said this thing went up and therefore this thing would go up. Well, no, that's not, we found the opposite is true, that this other thing that could have been a counter explanation went down, and where it had no relationship there. But then again, of course, be careful with that logical fallacy. Avoid the correlation equal causation thing. That is a logical fallacy also, in those kinds of things. So there's a lot of those kind of subtleties there to be careful with the reasoning part of this. Muller, for example, collected data on the inclination of Earth's orbit over a 100,000-year cycle, correlated it with the occurrence of ice ages, ruled out the plausibility of orbital eccentricity as a cause for the occurrence of the ice ages, and inferred that the bounce in the Earth's orbit likely caused the ice ages. That was a conclusion. Yeah, so Muller's ultimately referring to what became named here as the Milankovitch cycles. That is an important cycle. It's like a 21,000-year thing. Actually, that has to do with the bounce in the orbit, because the orbit does ever so slightly shift every so often. Anyway, Putnam uses multiple methods to subject to rigorous testing his hypotheses about what affects the success or failure of democratic institutions as they develop in diverse social environments to rigorous testing, and found the weight of the evidence favored the assertion that civic tradition matters more than economic affluence. Okay, so this is a couple of different things here about the method. Method and reasoning is really tied together. That is the important thing that I want to say on that first part of that, is the method you're using and the reasoning to get to the end there are really, really important. So that is also where the concern that I had in the prior video about method being designed to get a specific desired answer to a question can have a problem, because that's where your reasoning has to be very clear, and you have to be very devoted as the scientist to just finding the truth when you're thinking about the reasoning for something, rather than finding the answer that you want. Let's put it that way. A lot of times it's not going to be the answer that you want to hear. And actually, there's a bunch of studies in the past where folks have chimed up and said, this isn't what I thought the answer was going to be. Here, I thought it was going to be this, but the evidence and everything I constructed said that. That's a great scientist that does that can say that. I had the reasoning, I thought it was going to be this, and my reasoning was proven false, and, this is what it actually turned out to be, and here's the reason why I think it turned out to be that. And you know what? It's not what I wanted to see. It's not what I thought it would be. I have that happen all the time, unfortunately. Sometimes it's unfortunate when I have to go tell somebody that, and it's like, nope, it's not what I thought it was going to be. It's not what they thought it was going to be. It's this. Sorry, that's just what it is, and we figure out how to work with it, kind of thing. So reasoning and method are really, really strongly tied together. The principle itself has several features worthy of elaboration. For the first thing here, assumptions underlying the inferences should be clearly stated and justified. Moreover, the choice of design should both acknowledge potential biases and plan for implementation challenges. This is, again, why method and reasoning, the third and fourth principle, are really strongly connected together. The assumptions here, for the method often also are related to the assumptions you make on your inference. And so you really have to clearly state them and justify them. And this doesn't happen as often as you think it does. There's a lot of implicit assumptions that are made in some papers. There's a lot of implicit assumptions that are made. I can go into some depth on that, but I'm not going to for this video to try and keep it brief. Whoopsie. And those I don't prefer it when I see an implicit assumption. I often ask when I see that in peer review, or I try to ask when I see that in peer review, that you're implicitly assuming this. Can you justify that that's a good assumption here? Or can you explicitly state that, get it into the paper somewhere? Choice of design should both acknowledge potential biases and plan for implementation challenges. Sometimes your method is not easily implemented. Sometimes your reasoning is not easily implemented. You got to account for that too when you're putting together your reasoning for something. Acknowledging potential biases. Yeah, you got to acknowledge your own bias for one thing as a researcher, but you also have to acknowledge any biases the method may have produced. Any of those kinds of things that could be going on. The choice of the study design, the study methods that you use is incredibly important to the reasoning, like I said. Estimates of error must also be made. Claims to knowledge vary according to the strength of the research design, theory, and control of extraneous variables, and by systematically ruling out possible alternative explanations. Although scientists always reason in the presence of uncertainty, it is critical to gauge the magnitude of this uncertainty. In the physical and life sciences, quantitative estimates of error associated with the conclusions are often computed and reported. In the social sciences and education, such quantitative measures are sometimes difficult to generate. In any case, a statement about the nature and estimated magnitude of error must be made in order to signal the level of certainty with which the conclusions have been drawn. If you're seeing in studies, like the Intergovernmental Panel on Climate Change has this a lot now, high confidence, low confidence, medium confidence, things like that. That goes to the issues of error and uncertainty regarding the conclusions that have been made. You can see this actually, I think it's very clear, and actually a lot of the IPCC reports are getting very transparent now about when they make a statement, they tack onto it, we have high confidence in this, we have low confidence in this, all those kinds of things. So it's those kinds of things you should absolutely be doing that as part of your reasoning, and say, we think this is the reason why, and we're really strongly confident of it. And often that comes with numbers and estimates here. Sometimes it just comes, sometimes some of the reports, like with IPCC, it comes from different studies, and they're collating a whole bunch of studies, and the result there is, they're looking at, one study says this, another study says that, so commenting on the scientific community as a whole, they might say, we as a whole don't have as much confidence in this as we do in that. That's a whole other way of looking at it, but it is a statement regarding the error and the uncertainty around the conclusions that you're trying to make, or the statements that you're trying to make based upon your logical chain of reasoning in here. So you have to account for the fact that there's some measurement error. You have to account for the fact that you don't live in a world where it is something that is always in a lab, that there's something that's going to possibly confound things. And so you have to account for how certain are you that this is the reason why. And if you're not accounting for that and you're just saying, this is the reason why, you're not practicing good scientific inquiry. If you're doing that, you're just you're pushing an activism kind of bent. You have to have statements of confidence in here, and often it is numerically based with, often the physical sciences anyway, it is numerically based. If you've seen those images with the error bars or something where you have a squiggly line in the middle with a range of shading or something like that, those are all estimates of uncertainty that have to be there. They should be there anyway, at least in good studies, in my opinion there, but that is a suggestion here for sure. Most importantly, the reasoning about evidence should identify, consider, and incorporate, when appropriate, the alternative competing explanations or rival answers to the question. To make valid inferences, plausible counter-explanations must be dealt with in a rational, systematic, and compelling way. The validity or credibility of a hypothesis is substantially strengthened if alternative counter-hypotheses can be ruled out and the favored one thereby supported. Well-known research designs, economics, So we'll get into that and some of the biases examples they've got below that, some of the counter explanations that some people can put out there. But I will comment, this is actually more important than most people think here, and I agree with him, it's one of the most important things. If you're doing this in your logical chain of evidence and reasoning, you need to be able to try and put in there what's a counter hypothesis that could happen. What is it? What is the counter hypothesis? Kind of anticipate it if you can. And admittedly, this is really hard to do because unless you're looking at the full breadth of literature, sometimes you don't know that there's this other hypothesis over here that somebody posed, and so you need to. Somebody may come back and challenge you. Well, what about this study? That's totally fair to have happen. And so educational. And so the thing here is. Can you account for these kinds of things? And particularly some of these kinds of things, one of the things they ask for people to account for is selectivity bias. The idea, and this is particularly to economics and statistics and a few other things here. Selectivity bias is the counter hypothesis that the selection caused the outcome, not the treatment. So, for example, with experimental things with medicine and what have you, did you select particular people? Did you select particular things inadvertently? The participant caused the outcome. That the participants in the experimental treatment systematically differed from the participants in a traditional control condition in ways that mattered importantly to the outcome. A cell biologist, for example, might unintentionally place select heart cells with a slight glimmer into an experimental group and others into a control group, thus potentially biasing the comparison between a group of cells. This potential for a biased or unfair comparison arises because of the shiny cells that could differ systematically from the others in ways that affect what is being studied. Selection bias is a perverse problem in the social sciences and education research. To illustrate, studying the effects of class size reduction, credentialed teachers are more likely to be found in wealthy school districts that have resources to reduce class size than poor districts. This fact raises the possibility that higher achievement will be observed in smaller classes due to factors other than class size, teacher effects. Random assignment to treatment is the strongest known antidote to the problem of selection bias. So this is where randomized trials come in for clinical trials with vaccines and what have you. This is why we do randomized trials. You don't pick a group of people who are known to be resistant to side effects. You pick just random bunch of people to assign them to a control group. You pick a random bunch of people and you assign them to the folks who get the vaccine in testing in clinical trials. And that is for deliberate reason. Even the person who receives it doesn't necessarily know that they've received it. Somebody has a record somewhere because obviously if something goes wrong, you need to be able to treat somebody, but that's the reason for a lot of these kinds of things. So that's one particular example. And they are right, it does tend to be more of a problem in social sciences and education related research than it does to be in physical sciences. We don't often have that problem with selection bias in physical sciences, but we do keep an eye out for that kind of thing too. A second counter-hypothesis contends that something in the research participant's history that co-occurred with the treatment caused the outcome, not the treatment itself. For example, U.S. fourth grade students outperformed students in other countries on the ecology subtest of the Third International Mathematics and Science Study. One popular explanation of this finding was that the effect was due to the schooling and the emphasis on the ecology in the U.S. elementary science curricula. A counter-hypothesis, one of history, posits that their higher achievement was due to the prevalence of ecology in children's television programming. A control group that has the same experience as the experimental group, except for the treatment under study, is the best antidote for this problem. So that goes again to control groups kind of thing. And it is an issue. You've got to make sure, it's history there. This is also where sample size becomes important, because if it's like a very small sample, you can inadvertently catch a whole group of people who had both of those things go on in their history, and so then it becomes really, really hard to tell what the reason why. So things like that, you want to account for that too, with your logical chain of reasoning with the design of your study. A third prevalent class of alternative explanations contends that the outcome was biased by the measurement used. For example, education effects are often judged by narrowly defined achievement tests that focus on factual knowledge and therefore favor direct instruction in teaching techniques. Multiple achievement measures with high reliability and validity help to counter potential measurement bias. And we do have this problem too in some of the physical sciences, like when you're doing evaluation of something, there's multiple measures by which you can evaluate climate models and projections, or the accuracy of weather station data, for instance, versus observations, or satellite data versus weather station data, any number of different things. There's things like that here. So in our study, so there's multiple measures of something, multiple data points, multiple types of data that are interrelated, or sometimes not even related to each other at all, can be really helpful in countervening that. So that's why, again, method construction and the chain of reasoning here needs to account for these possible counter hypotheses as much as possible. Because again, that's the thing, is there's such a breadth of scientific research now, and quite many people who are doing science, it's sometimes extremely difficult to be able to capture, to think of everything when you're putting together a study, or doing the results of thinking of things why. And that's why it's also often helpful to have collaborators who are a little bit older, who have been around for a long time and read a lot of these things that you might not have read yet. The Tennessee class size study was designed primarily to eliminate all possible known explanations except for reduced class size and comparing the achievement of children in regular classrooms against achievement in reduced size classrooms. It did this. Complications remained, however. About 10% of the students moved out of their originally assigned conditions class size, weakening the design because the comparative group did not remain intact to enable strict comparisons. However, most scholars who subsequently analyzed the data were limited to suggested that the infidelities did not affect the main conclusions of the study, that smaller class size caused slight improvements in achievements. Students in class sizes of 13 to 17 outperformed their peers in larger classes on average by a small margin. So that comes to that particular study. But you're going to have that happen. That is a particularly important part, is that, as we scrutinize each other, we're going to think of counter hypotheses for why certain things happen and what happened here and there versus others. That's totally normal. But how you get to that point of even having those discussions is having a logical chain of reasoning going on here. And that's an incredibly important part, and it's very, very linked to the method of the study, and the method used is linked to the question. So it all links back to the question that you're asking, whether it's a significant question. But regardless of the question that you're asking, and the hypothesis you pose, which again is a hypothesis, it might not be the desired answer to the question, because again, you got to remember carefully, it's when you're drifting far away from scientists into activism, it's drifting into activism often because you want a particular answer to be the answer, rather than actually the answer that it should be, or the answer that it is. Let's put it that way. So yeah, that's the fourth one. So we've gone 1 through 4. One being the significant question that is empirically testable. 2 being linking that research question to the relevant theory somehow. Third one being a method that actually answers the question, helps you answer the question. And the fourth one now, the important chain of reasoning that is explicit, coherent, and replicable, that helps to give you strong scientific inference here. And of course, make sure you avoid logical fallacies. The woke do logical fallacies quite often. Don't go in the woke direction. Anyway, if you like this video, please subscribe to this channel. Comment below your thoughts on this. 2 more videos to go in this series on the guiding principles of scientific inquiry. Until next time, I'm Adrian. Stay curious, my friends.